Hello everyone, welcome to day one of our factoring unit. So today we're going to review factoring that you would have seen in prior courses. It's going to be GCF, or greatest common factor, dots, difference of two perfect squares, and grouping. Alright, so when factoring, the first thing you want to do is look for a greatest common factor. So when I look at example 1, I notice a common factor of 6. So what I can do is divide both 6x and 6 by 6, and I'd be left with an x plus 1. So sometimes teachers will call this reverse distributive property, because if you were to distribute the 6 back to the x and the 1, you would get 6x plus 6 back. And that's how you can double check your factoring. Okay, moving on to the next one. Between the 15 and the 5, I would factor out a 5. Because each of those I can divide out. Now when it comes to variables, you actually take the lowest power. So you can take an x squared out of an x cubed, but you can't take an x cubed out of an x squared. Likewise, I'm going to take a y out and a z out. Now, again, it's like reverse distributive property here. You have to get this back if you were to distribute. So 5 times 3 is 15, x, y squared, z squared, or again, you're just really dividing this by this GCF that I came up with, minus, now this happens to be exactly the same thing, so minus 1. Okay, so again, you can double check. If you multiply, again, you're multiplying variables with the same base, you would add the exponents. I see that x squared and x to the first would give me x cubed, y to the first, y squared gives me y cubed, z to the first, z squared gives me z cubed. Okay, moving on to example 3. Looking at the constants of a 6, 12, and 3, the common factor number-wise would be 3. And then again, I'm taking the lowest powers, so C, D. So I just silently went through and divided each of those by 3CD, or another way of thinking of it is I thought, okay, 3CD times what gave me 6C cubed D back? What times 3CD would give me negative 12 C squared D squared back, and that would be negative 4CD, and so on. Now, at number 4, what I'm noticing is a greatest common factor of b minus 2 in the parentheses. So just like how if you had something that looked like this, 3a plus 3, oops, let me write it like this, 3a plus, I keep wanting to write 3, 3a plus 4a, a common factor could be a. You could rewrite it like that. The b minus 2 is your factor that you're pulling out and writing once, and that leaves you with 3b minus 4. Oop, my pen wasn't writing for a second there. So this is what's leading us into what's called our factor by grouping method. Factor by grouping is typically used with 4 terms, and it's when we group the binomials, factor out a GCF, or greatest common factor, for each set of binomials, and then factor out what will end up being what I call the common binomial. And then we'll write our final answer with 2 sets of parentheses. All right, so looking at example 1, okay, I'm going to group my binomials just like that. Out of the first 2, I can pull out a C. Out of the next 2, I can pull out a positive 4. Now what I want you to notice is that you end up with a common binomial, we call it. That's actually your GCF, essentially, of the factoring that you just did, and relates to what we did up here at number 4. So what I can do is factor out that GCF, which again I'll call that the common binomial, and then that'll multiply what I call the leftover, which is c plus 4. Okay, moving on to number 2. I can pull a p out, and I can pull out a -9, it looks like. Notice how I did -9, not +9, okay? Because you need these binomials to match in order to end up factoring. So this is my common binomial, and this is my leftover. Okay, you don't have to write the common binomial first. I could do p minus 9 times 2p minus 3, and that would be fine as well. Okay, multiplication is commutative, so your factors can come in any order. Okay, moving on to 3, I can factor out a 6. And it looks like a 2y. Okay, again, there's your common binomial of x minus 2. So this would factor to x minus 2 times my leftover, 6 plus 2y. Ooh, actually, you know what? I'm just realizing something right now. And this is actually a really good learning experience. In this, there's actually a GCF of 2 between these that I really should have taken care of to begin with, but I didn't. I'll just take care of it right now. If I factor a 2 out of that 6 plus 2y, that would be 3 plus y times x minus 2, and that's completely factored. Okay, so again, really what I should have done was taken my own advice that I said before and factor out a GCF from all of them if I can first, which, again, all of those could factor out a 2. And that would leave me with 3x minus 6 plus xy minus 2y. And then I could have factored and grouped from there. So that's where I'm pulling out a 3. And I'm pulling out a y. There's your common binomial again. Y plus 3 or 3 plus y, however you want to write it. And you'll see that that's exactly the same thing over here at 3. Okay, so by factoring out the GCF and then doing grouping, or vice versa, essentially in the first way I did this, this is what's called completely factored, where every single factoring technique that I can employ has taken place. Okay, if I do number 4 off to the side here, okay, I'm noticing everything here can be factored out with a 5. So that's 5 times ax plus 2ab plus bx plus 2b squared. And then I'm going to group from there. So it looks like out of the first 2 terms, I can pull out an a. So x plus 2b. And the next 2 terms, I can pull out a b, it looks like. X plus 2b. All right, x plus 2b's are matching. That's your common binomial. So I have 5 outside and front, my common binomial of x plus 2b, and my leftover of a plus b. Ooh, I hope I didn't say radical in that last word. I feel like I might have. My common binomial. And that's completely factored. All right. Okay, taking a look at number 5. I have 3bc minus 2b minus b plus 15c. Out of the first 2, I can pull out a b. Out of the next 2, I can pull out a 5 and maybe a -5. So here's what's tough about what I have listed right here. 3c minus 2 and 2 minus 3c are actually not mathematically equivalent. That's like saying 2 minus 3 is not the same thing as 3 minus 2, right? 1 equals -1, 1 equals +1. So this takes a little bit more thought. Instead of factoring out a negative 5, let's make that a positive real quick. that would change this then to a negative and that to a positive. Let me just rearrange this now. Okay, negative 2 plus 3c is the same thing as 3c minus 2, and now those look like they go together. They're exactly the same, so we end up with 3c minus 2 times b plus 5. All right, last one on this page. Looks like I can pull out a 9f. So g minus 5 and a negative 7. Now, sometimes students will stop there and they'll be like, okay, I'm done. I factored completely. I factored it. That is not completely factored. You just did the first step in your factor by grouping. Again, this is your common binomial, so you need to take another line, write the common binomial, times the leftover binomial. And that's factor by grouping. All right, moving on to the next page. We're going to review dots, or difference of two squares. Keep in mind, these are your perfect squares. I'll highlight them in green. These are your perfect squares when it comes to variables. So pretty much anything with an even exponent is a perfect square because you can take the square root of it nicely. So when we figure out how to factor dots, you must have a binomial where each term is a perfect square. It must also involve subtraction. Hence, that's what difference stands for, subtraction. You take the square root of each term, and then your final answer is going to be with the parentheses, but one will be positive and one will be negative. And I'll actually remind you in a second of what that's called. So coming on down, something basic that you would have seen in Algebra 1. X squared minus 4 is just x plus 2 times x minus 2. Okay, now you don't have to write this, but here's why. I'm just going to do this off to the side. Let's actually FOIL this out. If you were to do FOIL, you would get x squared minus 2x plus 2x minus 4. And those inner and outer terms would drop out, and you'd end up with x squared minus 4. So that's why this is the appropriate factoring. Okay? Now, there's a word for this that we've learned last unit where they look exactly alike except for one's a positive and one's a negative. Hopefully you should be thinking to yourself, these are called conjugate pairs. Conjugates. We talked about them last unit when we did rationalizing of those irrational binomial denominators. Okay, so y squared minus 81 is just y plus 9, y minus 9. Because all I'm doing is taking the square root of each part to end up getting the y and the 9. Now, be careful. Some students will rearrange this. It's actually in the order given. So 7 minus x, 7 plus x. So because the 49 came first, the 7 would have to come first. Otherwise, you'd technically be off by a negative. Now, I deliberately did the subtraction first and then the addition because sometimes students will be like, oh, does it always have to be plus minus? No. Again, multiplication's commutative, so the factors can come in any order. So I just deliberately mixed it up right there. But I do want you to make a little note here that this is not equal to x plus 7, x minus 7, because that equals x squared minus 49. So order does matter with subtraction. Like I said, subtraction is not commutative. 2 minus 3 is not the same thing as 3 minus 2. All right, so we keep moving. Okay. Square root of 4x squared is 2x. Square root of 25 is 5. Okay. 4x plus 7y. 4x minus 7y. So this should be pretty easy. Again, one's plus, one's minus. I'm just taking the square root of each of them, amending it with conjugate pairs. Now this is not equal to a plus b times a minus b. You know why? It's addition, okay? Specifically, again, it has to be subtraction when you're doing this. A squared plus B squared is actually not factorable. But I threw it in here just to make sure you were paying attention, okay? So just to clarify, A plus B times A minus B would be A squared minus B squared. Okay. What about fractions? Well, 9's a perfect square and 16's a perfect square. So this is 3/4 minus 5z squared. That's the square root of both parts of that. And now I just need to multiply by its conjugate pair. Done. Okay, so same thing here. 6/7x plus 8/9y. Once I have one part of it, I just need its conjugate pair. Okay, now this one's interesting. When I look at this, I actually notice that I can factor out a GCF of x to the 4th. And that is then 25x squared minus 121. And this helps me factor it completely. So now this is 5x plus 11, 5x minus 11. Again, factored completely. Okay, if I look at 10, okay, I can take the square root. Well, actually, let's do this. I can factor out a 2 from each of those, right? I think that's the biggest perfect square. Oh, no, what am I thinking? A 4 would be better. All right, so I'm going to factor out my GCF of 4. So that would be 9a to the 4th, b to the 6th, minus 16x squared, y to the 8th, and then I can do dots from there. So remember, I'm just dividing these exponents by 2 when I'm taking the square root. Okay, once you figured out half of this, you just have to repeat it and then make one sign the opposite. Okay. Now skipping ahead to something like 13, okay, where this looks kind of interesting. It has x plus 2 squared minus 1. Technically, this is a perfect square because it's something being squared, and this is a perfect square as well, because 1 squared is 1. What I'm going to do is actually make this look a little bit nicer. Let's pretend a, just another variable, equals x plus 2. That would mean this is equivalent to a squared minus 1. Now, in terms of a, I can really easily factor this and say it's equal to a plus 1, a minus 1. Okay, but what did I really say a was? A is equal to x plus 2. So I'm just going to substitute back in x plus 2 for a, and now that's factored. Okay, so likewise, let me actually come over to 17. Let's call it a again over here where the x plus 1 is squared. So this is 16 minus 9a squared, which then I can factor that to 4 minus 3a, 4 plus 3a. Now, it's not really a though, it's x minus 1, so I'm going to go and substitute back in x minus 1 for a. All right, coming back over to 16, okay, dots, again, I'm just taking the square root, so this is x cubed minus 5, x cubed plus 5. And jumping back up to 12, let's see, is there a GCF I can take out? I'm thinking I can pull out an x to the 16th. That's my GCF, so then 16 minus 25, x to the 4th, y to the 18th, and then I can do dots from there. So 4 plus 5, x squared, y to the 9th, 4 minus 5, x squared, y to the 9th. Okay, I skipped 11 in there. Let me just try to see if I can squeeze it in there. T plus 2 over 5, t minus 2 over 5. So lots of square roots, lots of conjugate pairs, and ultimately that's it. All right, now I just want to give you a heads up on the homework that 21 and 22 are a little tough, because if you initially try to do your factor by grouping, I don't even see a GCF between the first two terms here. But there's nothing stopping you from trying to reorder some stuff. So like I'm noticing that I can put the 4's together. So I have 4ay plus 4cy minus cx minus ax. And then from there, I see GCFs that I can factor out. So that's my advice there. Likewise, at 22, I'm not going to be able to factor anything out. So I'm going to have to do a little bit of rearranging. So maybe I want to put like y's together and x's together or 3's together or something. So like I'm thinking I could do by plus xy by getting these two together. Negative 3x minus 3b, and then that should work from there. One last thing I want to mention too is if you end up with common binomials like hypothetically something like x plus 2 versus 2 plus x, recognize that those are equivalent. But if you have something like x minus 2 and 2 minus x, those are not equivalent. Okay, so I hope this video helps. You just need to finish up this assignment and do some factoring practice.